at NCC Group as a security consultant. It's really cool because whenever I'm not hacking on client stuff, my company gives me time to perform research and just pursue my own interests, and that, like some of that free time, produce this presentation and the work within it. So yeah, it's a really cool place to be. Our booth is literally right outside. The door's there in the back, so afterward, if you want to hear more about what we do or check us out, just stop by the booth. We have a really friendly recruiter. And then I'll be there too to talk to you guys as well. There's a few other of us here. So anyway, yeah, so how many people have been playing their favorite first-person shooter? They're doing really well, you know, this is fun, and then bam, you get sniped from across the map. Like, right? This has probably happened. I know it's happened to me, it's probably been happening to you guys too. Yeah, and this person that sniped you, like, there's no way they can even see you. They're on the other side of the map. There's too much fog. They're obviously cheating. So if you're like me, that's like, oh, that's really lame. Like, I was doing good, I was on the street, and this guy's cheating, he took me out. How else did he get me? So if you're also like me, you probably thought, you know, that's kind of cool, like from a technical standpoint, like how does somebody come up with that and like make a cheat like that work? So yeah, what we're going to be talking about today is a little bit about how games can be reverse engineered. Specifically, you know, step one of writing a game hack is reverse engineering the game. So we're going to talk about how you might reverse engineer a game. And I also want to talk about a tool that I wrote to automate part of this reversing process that saves hours of time and makes things a lot easier. So first of all, what are game hacks? I mean, I'm sure you guys have all seen them before. I want to show off an example of a game hack that I wrote personally. This is for a game called Battlefield 2, which was popular about 10 years ago. So my point of view is in a helicopter. If you look, I don't know if the mouse is on. Yeah, it does. That's an enemy helicopter piloted by an AI-controlled player. So I'll pop open this YouTube video. Let's see how visible that is. That's like pretty good. Yeah, so what I'm going to do here is, in a second, I'm going to switch to the gunner seat and activate my TV-guided missile, which is a particular weapon that this attack helicopter has. And the hack that I wrote is actually an aimbot for that missile. So normally, the way that you would use the TV-guided missile is once you switch into the TV screen mode. So there, now I'm in the now I'm about to fire off my TV missile. You can see there's a crosshair. Activate my little red pointer thing. Yeah. Oh, it goes away. Anyway, so this crosshair right here is what normally you'd use if you're not cheating. You normally just click on the screen where you want the missile to go, and you can do that repeatedly throughout the missile's flight. I didn't want to do that, so I wrote a cheat to do it for me. So you'll see here in a second, that crosshair is going to be moving around as the missile's flying, and it's going to be, whoops, there we go. It's not going to aim directly at the enemy helicopter because I programmed the cheat to aim slightly ahead. So you can see now that the missile's been fired against that enemy helicopter right there, and then the crosshair is here, and it's aiming ahead of where it's going to be. It's leading him a little bit, so it has a better chance of hitting him. So you can see as it's flying to the target, and it takes him out. And all I was doing there was clicking the mouse, because I hadn't programmed the cheat to click the mouse for me. But all the aiming, all the controlling of where the crosshair goes is done by the cheat. So one more time, slow motion. Oh, that's the wrong one. Here we go. Half speed. Let's see that again. We'll switch over into the TV missile mode. And now the aimbot is controlling where that crosshair is, so it's figuring out, you know, my position. It's figuring out the position of the enemy helicopter, and then it knows exactly where to aim. So kind of cool. How's something like this done? So how does a cheat work? So typical cheat architecture, not all cheats are made this way, but something you see a lot is a cheat developer will write a DLL that's going to get injected into the game process. So in this case, this would be Battlefield 2. This DLL gets injected, and then from there you have cheat logic that is going, and it might, I mean, this is kind of like pseudocode, and it might look something like this, where it's saying, okay, get each player, if they're an enemy, then you get their coordinates, and then, so this imaginary hack, this hypothetical hack, is going to be like an extrasensory perception hack, where it might show you where on your map or whatever, where your enemy players are. Some of you might not normally be able to see is where my enemy is located. This cheat's going to reveal their locations for you. It's just a hypothetical cheat to demonstrate cheat architecture. So to take this, get into a little more detail with this. So for example, that getPlayerByIndex function, it's got to figure out where in memory the enemy players are, or else how is it going to be able to determine if they're an enemy player or figure out their position? It's got to read their coordinates out of memory. So how does it do that? So if you have this hypothetical function that's getPlayerByIndex, what it's going to do is read some value from a predictable address. It might be in static memory somewhere. And then it might dereference that to get a pointer to some game management object, let's say. And then at some offset within the game object, there might be a pointer to a linked list, which then contains, so each node of the linked list might contain pointers to player objects. And then from there, you get the coordinates, and you can see this getCoordinates method is part of a player, like an enemy object. And then from there, it can get the player position out of the player object. So that's how these functions might work. Basically, like the key concept here is that we're starting a predictable address and performing then a sequence of offsets and dereferences down to the data that we're actually interested in, which in this case is our player's position. So I put some text on this slide because it's actually like a key concept for the rest of the talk. The sequence here, the pattern of offsets and dereferences is crucial to making this work. And the interesting thing is that the sequence, the specifics of that pattern is formed by the structure of and relationships between the game objects. So these are objects, of course, that have been programmed by the game developers. It's our job as reverse engineers to figure out the specifics of how those objects have been implemented, so then we can traverse them ourselves and get the data that we're interested in. So this orange thing, all these orange squares, are just kind of like a little more detailed version of what was on the previous slide. So these little orange rectangles have been expanded to include a little more information on this slide. So here might be like our first predictable address. So let's say some predictable address that's at a static offset from the executable base image in memory. This predictable address is always going to contain a game object pointer. Game object pointer obviously points to the game object, which let's say for in this example at an offset of 0x8 contains a pointer to a linked list. And then from there we can traverse that linked list as we do. And you'll notice that each node has now pointed to a player object at an offset of 0x4. So now we can go from a predictable address and traverse this sequence of offsets to get to given player objects that we're interested in. And once we get our player objects, let's say, for example, we know that the player's position is in data that's at 0x40. So does this make sense so far? Any questions or anything I should repeat again? Okay. So how do we find these sequences? And step one, I guess there's probably more than one way. Typically what I do is I start by finding the address of the data of interest. So in this video, I'm going to show, let's see, that's big enough I think. So what we've got here is Battlefield 2 on one part of the screen, and then over here, this is a program called Cheat Engine, which is just a memory scanner. Its whole job is to scan memory for you, and it lets you search for certain values, and then try to find parts of memory that have data you're interested in. So I'm going to use that on Battlefield 2 to try to isolate where the game is storing the coordinates of our TV missile crosshair. So what I'm going to do is, the first thing is I will do an initial scan of memory, and that's just going to record all the values in the game's memory as it's going to interpret them as floating point types. And then once I've recorded what every value is to start, then I'm going to start moving the TV missile crosshair around in the game. You'll notice now that I've moved it off to the right here, and I'm kind of making an assumption that the TV missile crosshair coordinates are done in such a way that when you move the TV missile crosshair to the right, the x coordinate is going to be increasing, and when you move it back to the left, the X coordinate is going to be decreasing. So as this video is playing, I'm running scans. Let's see. Might be a little bit small. I'll make this big now so we can see. Okay, so now you can see I'm searching for values that have increased. Now I'm going to switch it to values that have decreased. And that's because I moved the crosshair back over to the left. So we're switching back to Battlefield 2, moving our TD missile crosshair even more to the left, and then looking for values that have further decreased since the last scan, so on and so forth until we finally narrow down a reasonable amount, a reasonable number of addresses that could potentially contain the data we're interested in. So I don't know if anyone noticed when we first started out, I'll go back here, that the number of addresses found at the start is like 272 million. That's way too many to go through manually. And even after the first couple scans we perform, we're still at 70,000 potential addresses of the data that we're getting. That's just way too many to go through by hand. So keep doing this, keep moving the crosshair back and forth, and then re-performing the scan for values that have changed accordingly. Eventually I get down to about 21 potential values. Now this is really manageable. So notice how these values change as I move the TD missile cursor around. Let's see that one more time. So you notice where the TD missile cursor is over here. And now as I move it over, you see these values increasing. So that tells us we're on something. We have a lot of these candidate addresses seem to correspond to the movement of our TD missile crosshair, and that's good. So what I'm going to do to test this hypothesis is I'm going to select some of these addresses from up here into my little sandbox, and then I'm going to double click on the value column, and it's going to let me change the value of the data at that address to whatever I want. So here I'm going to change it from 226 to, let's see, -50. Now watch, as soon as I click OK, watch what happens right about here. That TD missile crosshair just snapped over, and that tells us that now we are in control of the coordinate.
That's really cool.
Yeah, so now we've isolated where in memory the game is storing this information, and if we find that if we write to these addresses, we control the behavior of the TD missile crosshair. And that's really good because obviously if we're running a TD missile hack, one of the things it's going to have to do is just control that crosshair for us. So now we have addresses of interest. What do we do from there? It would be nice if we were done there, like, oh great, we have our addresses, like we can just start writing our cheat. Fortunately, usually not the case. That's because when you think about how this application might be coded with objects allocated dynamically on the heap. Every time we start the game, that address that stores the data that we're interested in this case, the coordinates of the TD missile crosshair, it's going to be completely different. So we're kind of like, can't just throw our hands up, but we think about what we might do next, and that would be to, we think, well, okay, so how does the game figure it out? Like, how does the game keep track of where that data is? Like, obviously the game's not crashing. Every time you try to move the crosshair, it must have a way of determining how to access that. So what we can do is we can observe the execution of the game and learn what it's doing, and then try to copy it later on when we write our cheat. So instead of a cheat DLL here, this could be this is the game executable, this is the game code, and here's that hypothetical function that we're going to use in our cheat that we want to copy. It's doing the same thing. It's going to be starting at some predictable address, performing a sequence of offsets and dereferences in order to get the player's coordinates. So in this hypothetical game code here, it's going to be checking that players are inbounds or out of bounds. Just a hypothetical example. So after we've determined the address that we're interested in at a particular point in time, we can set a memory breakpoint on that address. So this is using OllyDebug, which is a debugger that, if you're not familiar with, you're probably familiar with debuggers in general, and it's just the same sort of thing. So I'm going to go to the address that we found last time. So that address, I don't know if you remember from that video of using cheat engine, but the address we came up with was 46D4C4C. So we're going to go to that memory address in our debugger's hex dump window. So that puts us right here. And we're going to use OllyDebug to put a memory breakpoint on that address. So now anytime Battlefield 2 attempts to read or write from that address, that memory breakpoint's going to get triggered and the game's going to stop. So you can see as soon as I set that, actually, execution pauses. And this would be because the game is frequently reading and writing to this address. Okay, so that's how you might set a breakpoint. Let's go to the next slide here. So now, step 3. Once we hit that memory breakpoint, then we might want to set a soft breakpoint, kind of before that memory breakpoint gets triggered. And since memory breakpoints don't necessarily get triggered by a specific location in the code, that notion of before is kind of fuzzy. You kind of have to do a little guesswork to decide, where your next soft breakpoint should go. But the point is, you want to put another breakpoint just prior to the instructions that cause your memory breakpoint to get triggered, because then you can see what the game was doing just prior to accessing the data that we're interested in this case, the coordinates of the crosshair. All right, so I'm just going to let the game run a few times. So it's still hitting that memory breakpoint every time I let the game run. So here's an instruction that is triggering our access violations, hitting a memory breakpoint. So we can see that at this time, ECX, the register contains the address of the TV missile crosshair's X coordinate, and then when it dereferences that and tries to read from it, that's going to trigger the memory breakpoint. That's cool. Let's put a breakpoint on that, and then let's put a breakpoint right above it. We're gonna see what happens when this function gets called. This is a Collisson subroutine. No idea what it does. Let's find out. It's happening right before the access of the data that we're interested in, so maybe it's something that we're interested in. So once we have set that breakpoint, we let the game run until the execution stops on the breakpoint that we just set. And then we're going to use the trace functionality to record every instruction that gets executed between our first breakpoint and our second breakpoint. So I'm going to hit trace into in the debugger, and it's going to snap down right away to the breakpoint that's just below it. And now we can go over and view the run trace that was just generated by doing that. So you can see here, 5 instructions happened between the call to that subroutine and then the actual reading of the data that we're interested in. So this is kind of interesting now. It gives us some insight into what the game's doing and how the game's actually going to access the data that we're interested in. So you can see that ECX contains the pointer to the data that we're interested in. That pointer came from ECX. You can see the instruction right above here. It moves value EAX into ECX. And if you look up here, you can see, okay, well, where did EAX come from? We look up 2 more instructions. And here we are, we're loading the address that is the value in ECX at this time, adding 38, dereferencing, and then storing that into ECX. So this is kind of our first peek into what those sequences, those offsets, and dereferences look like in terms of actual execution of instructions. So we can see here that the game is kind of traversing a small segment of that sequence that we're interested in. So that's awesome. We don't have the complete picture yet. Obviously, it seems like we work our way up to here, ECX plus 38, but what does that really get us? I mean, all we know is that at the end of our chain, at the end of our sequence, we add 38, dereference, and then that gives us a pointer to our to the data we're interested in. But I mean, like, what was here? What was ECX before we added 38 to us? We don't know at this point. But if you continue this process of kind of creatively guessing, where should I set my breakpoints to observe what's executing in the game prior to this point, you might be able to see, where the values are coming from. Or you could probably use a timeless debugger. I think there's some debuggers out there that you might have heard of. In Kira, it's called. Pretty cool as you step forward and backward in the execution. That would probably be really useful for something like this. I haven't played with it yet, though. But since if we're not going to use that, we need to just keep setting breakpoints above above in quotation marks, kind of like a fuzzy notion. But I guess prior to the execution of the code that we've already observed, to see more about how the game is traversing that sequence of instructions. So yeah, step 4 is basically just repeat that process until a predictable address is used. So you can see in this screenshot that up here, the game isn't reading from a register. This is a static address. This is a constant value, A08F60. Turns out this is like an important memory address in Battlefield 2. A lot of things can be accessed if you start there. But anyway, you can see that the game is dereferencing this constant value, storing it in ECX, dereferencing it, storing it in EAX. It looks like it's calling a virtual function there. Anyway, yeah, so you can kind of just see, what the game is doing and how it's, the pattern of offsets and dereferences that it's following in order to start from a predictable address like this one to get all the way down to the data that you're actually interested in so that you can access it later on. So some of the problems with this approach, as fun as manual reversing is, it's time consuming, it's very tedious, and you frequently run into dead ends where you kind of get lost or some value goes on the stack for a really long time. Like I don't know. I mean, maybe some people are better at this than I am, but I find that it can be frustrating at times, and it can take a really long time, and you don't come up with any results. So doing what I described manually might take me somewhere between hours or days or minutes if I get lucky, but typically hours. So let's write a program to do this instead. That program is actually a tool that I wrote that I'm going to talk about in a couple slides. But first, let's kind of summarize the approach that we're following, because we're going to distill the reversing algorithm out of that approach and then implement that in our tool. So basically, it worked something like this. We observed that register X was used to access the data of interest. So in that case, that would be ECX is our register X, and then observed that the value of register X was calculated by adding an offset to register Y, and then dereferencing. And in this case, register Y would be ECX again. I mean, you can see that the instructions are kind of juggling that value around. Here it goes, ECX to EAX, and then EAX back to ECX. But yeah, in this case, it's kind of register, Y. And then you can observe that the value of register Y was calculated by adding an offset to register Z. And in this example, we don't have a register Z yet because we didn't record enough of the execution prior to this code here. But if we did, and if we worked our way back up using that manual reversing process, eventually you'd start to see register Z and so on and so forth, up to a point where you get to your static value that's being dereferenced, and then you can stop. Okay, so here's a tool I wrote, and it basically just implements this approach. It does that reversing algorithm. It sets memory breakpoints and records execution in order to perform that analysis on the instructions that have been executed. So here's an action. So make this larger. So all you have to do is you enter in the process ID of the target, in this case is Battlefield 2's HID. That's what we're interested in. And then you enter the address of interest. So if you remember, this is not actually the same address of our TV missile crosshair coordinates. This is another data number that I selected out of the player object just randomly because I figured it might get read to or written to more often than the TV missile crosshair. So that might be better for demonstration purposes, just because it's going to execute faster. But so once I've done this, the game is then, so it set a breakpoint, and then it started recording execution. You see here that pretty quickly that memory breakpoint gets hit, and now what it's going to do is it's going to take all the instructions that it recorded the execution of, and it's going to start doing analysis on those to do that algorithm to figure out, okay, so like where did this value come from, and can I work my way back up to a static address. So we can see pretty quickly here it spit out some output. I don't know what to make of this, honestly. Like this is kind of nonsense. If you notice, it's outputting the same instruction over and over again. Which, I mean, that seems like, I think this might have a bug that I recently introduced and need to iron out. But that's all right. thing about this tool is it's not designed to be accurate 100% of the time. I just want it to give me the right answer faster than it would be for me to do it on my own. So we'll see here as you give it more time to let the game execute and record more instructions and perform more analysis, that the output starts to get more coherent. So here this we're starting to see stuff that makes some sense. So if you see this, you see that this is the address that we plugged in. That's the one we're interested in. We can see it was obtained by taking something in ECX and adding 30 to it and then dereferencing. We can see that the address of ECX came from adding 88 to ESI. So this is a load effective address. We're not actually really dereferencing. So you can think of this as adding just ECX plus these two put together. Not that important of a detail. Then anyway, looking up further, we can see, okay, where did ESI come from? Okay, ESI came from ECX, ECX came from ESI, EAX came from ECX, okay, and then EAX, ECX, whatever, anyway. Here you see another instruction that's kind of relevant to us, and it's telling us, okay, so something in EAX plus 4, and something in ESI plus 80. These are all, offsets that we're interested in, but again, it doesn't get us all the way back to a predictable static address. So let's sort of keep running and see if we get something useful, because ultimately, we have no idea, what ESI is. Well, actually we do, it tells you right here, but I mean, that's going to be different every time you start the game. So this is not particularly useful to us. Let it run for another minute or two. Right here at the end of the video, and this is in real time, by the way, so.
Did you write this in C? Is this using an API from the debugger, or?
C++. Yeah, and it's not using an API from the debugger. I actually have a slide later on that talks about like how it's implemented.
You're just accessing the memory directly from C++ right now?
Yeah.
Okay.
Yeah, so this is, actually, let me think of how this is doing. So this is external. Yeah, it's actually using read process memory for most of the reads from memory. Yeah, okay, so here we can see it spit out something that is really interesting to us, because look at this value right up here. This is A08F60, which is a static address. So what this is telling us is if you start at A08F60 and dereference, and then add 60 to that value and dereference, and then add 80 to that value and dereference, so on and so forth, you get down to the value that you're interested in. Now, looking at this trace right here, it's kind of confusing to see what's going on. There's a lot of instructions, there's a lot of additions and dereferences, kind of difficult to follow. And I noticed something when I was developing the tool is that sometimes that's just how the analysis gets performed, but it's not always like entirely relevant to you. So if you look down at this second trace here, you can see this is actually an analysis performed. This trace right here on the bottom is just a minimized version of what's up here. So this bottom trace is just this trace with some processing performed on it, and this one contains kind of like just the information that we're interested in. So if we analyze this one instead, we can see that we go from A08F60 static address, we add 60 and dereference, add 80, dereference, add 4 and dereference, add 88 and then add 30 and dereference, and that gives us a point to the data that we plugged in. I should have mentioned this earlier, but I guess I forgot. This address here is the value, is the address of our player's coordinates in memory for a particular, particular time that we're running this game. So now we can see, what this tool output, and it tells us exactly how to go from a predictable address. Like this is going to be the same every time. You can see it's a static value, and it's going to work its way down through this series of offsets and dereferences, and it gets us to our player's position every time. So this is really cool. So now we can see exactly how the game is traversing its data structures to access data that we're interested in. So we don't know exactly what those data structures are yet. We'd probably want to take a little bit of time to reverse those themselves. We don't necessarily even really need to know that to be able to access the data that we're interested in, which was, in this case, was the position of our player in memory. So that's pretty cool. So something that used to take me hours to do, I can now get out of this tool in a couple of minutes. So here again, I'm highlighting the relevant output from this tool. We already went over this, but you can see again, this is the sequence that's necessary to go from predictable location in memory to the location of memory that stores your player's position. So that's really cool. So this is the sequence that we need to follow. Does that make sense? Yeah, question?
So with position independent executables,
yeah.
That static address, is that going to change?
So that's a good question. Battlefield 2 is a super old game. Doesn't support position independent execution. So that's one of the things that my tool, I hope, will address and support in the future. So probably I'd be looking for instructions that start by dereferencing a value that is an offset to RIP, or the instruction pointer. I think that's the approach I'm going to follow for that. No, that's a good question though. So this Battlefield 2 is like a nice sandbox because it's not trivial. It's a fully fledged first-person shooter, but it's also not modern enough to support position independent execution. So kind of a nice testing ground for this sort of thing. So here I'm going to go back to the cheat engine. This is like a different aspect of the functionality of cheat engine. It lets you peruse memory. And what I'm going to do is I'm going to plug in that address, that's A08F60. And I'm going to see what address, this is inside the game's memory. I'm going to go down 60, dereference, as I'm just following the sequence here. I'm going to go down 80, dereference. Go down 4 and dereference. And then I'm going to go down B8 and see what's there. So I think that's kind of visible. What you can see there is what that's pointing to is this value that we've told cheat engine to interpret as a float is -284, and this is actually our coordinates in game. So another thing we need to know in order to write a lot of cheats, including bots, is the positions of players in memory. So this is awesome. Like we can go from a static address, same every time, right down to our players' coordinates in memory. That's pretty convenient. Alright, so now to get to these tool implementation questions. I wrote in C++, on top of the Windows API, and I used the Capstone disassembly engine in order to do some of the analysis on the instructions once they're recorded. So you might be wondering, why didn't I just, do this in Python? It might have been easier. Why didn't I write this as a plugin to some debugger? That might have been easier. And that's definitely true. However, I was looking for a good debugger to write this on top of, and I couldn't find one that kind of checked all the boxes that I was looking for, which were, I wanted something that had, a well-documented featureful API and supported 32 and 64-bit applications. I couldn't find one that really fit the bill. Maybe it's out there now. Maybe that would be cool to implement this tool there. But another thing was I kind of wanted to just do this myself from the ground up and learn a little bit about how to implement a debugger, and just gain more experience with the Windows API and C++. So kind of took the hard route and did it myself. And the tool basically features two classes. The first is a debugger class. The second is a tracer class. So the debugger class is in charge of setting the memory breakpoint on the address of interest, and then also recording the execution as that happens, as the game executes. And it does that by setting the trap flag in the CPU. Basically tells it to, after every single instruction that's executed, stop executing and let me know. At which point the debugger records the instruction that was just executed. And then it stores, all of those instructions until the memory breakpoint gets hit, at which point the tracer class takes over, and then it analyzes the recorded execution using the Capstone engine. And when it's analyzing, when I say analyze, I mean it's implementing that algorithm that we talked about earlier, where it's seeing, okay, so like the data that we're interested in was read from EAX, which, EAX is like data pointing to our data. All right, where did the value in EAX come from? And so on and so forth until you get all the way back up to where did that value come from? Oh, it's like a static address in memory. So memory breakpoint is kind of cool. I'm not sure if there's other ways to implement them, but basically what I found is that the way to do it is through page protection and then address validation. So here we tell Windows, and this is just kind of like a random snippet of code, but here we're telling Windows, okay, like don't let anybody read or write to the page that contains our address of interest. Windows says, okay, so every single time the game or whatever target binary we're studying tries to access this address of interest, an exception gets thrown, at which point the debugger class then checks and sees that the address that was accessed is actually what we're interested in, because there's, a page is going to contain more than just the address that we're interested in. So it's on our debugger class to then check and see if the address that triggered, the access to the address that triggered the access violation is actually the one that we're trying to set the memory breakpoint on. I guess that's the same size list. So yeah, and then the instruction, the execution recording I talked about earlier is done by single stepping using the CPU trap flag. So here we just kind of get the CPU, the flags for that thread context, and we just set a bit on CPU. We say, hey, like, don't execute any more than one instruction at a time, and let me know every time you do so I can record that. And then the tracer class, which analyzes the run trace, performs those steps with a reversing algorithm. And then when it's done doing that, it saves and prints the relevant instructions. So the tracer class is actually what's showing us that useful output. And one last, the other useful feature I was talking about that the tracer class does is it removes redundant instructions from the output. So here again, this is the same two traces from earlier. This one on the top is not reduced, it's not minimized at all. And this one is. So you can see that they have some instructions in common. This is from the same, recorded run trace, but the one on the bottom here is just leaving out some of the irrelevant instructions. For example, we don't really care that ECX was moved into EAX here, and that ESI was moved into ECX here. This isn't really relevant to us. We just we only care about the instructions that were used to get from point A to point B, and that's what the trace minimization does. So this is a lot easier for us to look at and interpret. Okay, one other thing it does, and I haven't touched on this at all yet, is vtable identification. So if we go back and look at our output, you see this last column here. This is outputting the vtable, a potential vtable pointer that's going to be that's going to be located at these values along the trace. It does that by checking the memory protections of values that are present in the trace. So it's checking the memory protections, on these addresses, and also the addresses that those point to. Okay, so what are vtables, and why do we care about this at all? Vtables are a way for, they're a common implementation for compilers to support virtual classes. So virtual classes are classes that leave the implementation of their methods up to their subclasses. So for example, if you're writing an application and you want to have different types of animals, you might make an animal-based object that can do things like move and eat. But since there's all different kinds of animals, and they all move different ways and they all eat different ways, when you're making, you can't just implement those methods in the animal-based class. You leave that up to the subclasses. So when you have like a cat animal or a bird animal, that's where you would define how those animals, those types of animals, those subclasses of animals would actually move around and stuff. So the difficulty with that is that the compiler at compile time isn't always going to know, what type of animal you're dealing with. Let's say you're calling the move method on some pointer to an animal object. And in your code you say, oh, this is an animal object, but the compiler doesn't know which method to call, which implementation of the move method to call, because it doesn't know what type of animal you're dealing with, actually. So what it does is it hides a pointer inside your inside the instantiated object in memory, and that pointer points to what's called a V table, which stands for the virtual method table. And the V table contains function pointers to the correct implementations of the virtual method. So all cat objects, let's say, are going to share the same V table that contain pointers to the cat-specific implementations of the move methods and the eat methods. And the same for all the bird objects. They're all going to, every bird object is going to have a pointer at the start of its memory to the bird V table, and then the bird V table contains the pointers to the correct bird-specific methods. So still, okay, why do we care about this? Well, one of the reasons is when we're looking at a trace, we can see where certain objects might be. Now, I've researched about it a lot. I've done a lot of reverse engineering on it, so I know off the top of my head that an AAC 530 V table corresponds to a player object. So now, as soon as I see this trace, I can kind of put it into context a little bit. I can say, oh, okay, I see here it's we're dealing, this was a pointer to a player object in memory. So it helps you make a little bit of sense of, what you're looking at, once you become more familiar with some binary. And also you can kind of see, potentially, maybe you're just curious, what's a virtual object and what's not, what's some other kind of data structure. And then from there you can kind of get, clever and use other types of clues based on your V-table values to try to learn more about the game, or whatever you're reverse engineering. So, for example, if let's say you're playing a game of Battlefield 2 with 32 players are loaded into your map, and then you do a memory scan for this value, the 8AC530, which is the pointer to the V-table for a player object, you'll get exactly 32 hits in memory. So that might not necessarily always, be true for all different kinds of objects. There might not always be a one-to-one correspondence between the number of, those objects and the number of that value, the number of times that value comes up in memory. But sometimes things like that can be helpful clues. So the way it does the identification of V-tables is it looks at the page protections for the potential V-table. So whatever this is pointing to, it looks at what's the page protection here, and then whatever this is pointing to, it looks at what's the page protection here. So V-tables are going to be in read-only memory. So if whatever is at the start of some value in our sequence points to read-only memory, like okay, we might have a V-table. This might be a V-table. So then we take a look at where this is pointing, and if this is pointing to executable memory, that's a pretty good indication that we've come across a V-table. Because obviously, our virtual methods are going to live in executable memory. So we can just kind of judge based on that whether or not we're looking at a V-table pointer. Obviously, it's not perfect heuristic, but I've never seen a false positive or negative with this technique, so it seems to work fairly well, fairly reliably. So, how's the performance of this thing? You've seen it in action. It's not exactly fast, and it might spit out a lot of garbage before it gets to the correct answer, but it's way faster than manual reversing. And then it's also faster and more accurate than Cheat Engine's pointer scanner. It's kind of funny because when I was setting out to make this tool, at first I wanted to check and see if someone hadn't already done this work. I don't want to spend all this time doing something that's already been done. Implementation for this already exists. I couldn't find anything, so I said, okay, well, I'm going to start doing this. Hopefully I'll discover that someone's already done this better than me. About halfway through coding it, I realized that Cheat Engine, which is a program that I've used before and that I've used a bunch, actually contains a feature I hadn't known about at the time called Pointer Scanner. Pointer Scanner attempts to achieve the exact same thing that my tool does, which is just get you from a predictable location of memory down to an unpredictable location of memory, where it's whatever data you're interested in is hiding. But Cheat Engine's Pointer Scanner does that actually in the complete opposite way that my tool does. So my tool works its way up a recorded instruction trace, so it observes the execution of memory and then works its way up to go from the the address that you're interested in back to a static address. And cheat engine pointer scanner actually works its way down by brute forcing all the potential pointer chains that could possibly exist. So it starts by looking at all of the values that are contained in static memory, and then just starts brute forcing pointer chains through some configurable level. So it might jump down 5 levels of dereferencing, and each time try doing offsets of up to 2048 or something like that. So it's going to do a lot of brute forcing, and hopefully one of those chains is going to actually by chance end up pointing to the address that you're interested in. So that's kind of cheat engine's approach. I found in my experience that the tool that I wrote, luckily for me, is faster and more accurate than the pointer scanner. I don't know, maybe it's just my own ineptitude when it comes to using this particular feature. I haven't used it too much, admittedly, but in my experience, the pointer scanner takes forever to run. It eats up a ton of, I think it uses up a ton of memory. And I don't know, it's just really performance intensive. It takes a long time, and it's not that accurate from what I've seen. It hasn't really ever given me useful results. So some of the stuff I want to add to make this better is support for 64-bit applications. Right now it only does 32-bit, so not super useful for the real world until I get that in there. Also support for position-independent code. That's going to be a good one to add for assessing, for looking at modern games, modern applications. And then just some fancy command line arguments. Like I want you to be able to save your output to a file, configure verbosity, do other configuration values like maybe the maximum number of instructions to store at a time. So if you store less instructions at a time, that might speed up how quickly the tool is running. But you might also kind of chop off the top of your sequence. You might not keep track of instructions that you need to keep track of. All right, thanks. So yeah, you can kind of play with those sorts of things. Yeah, testimonial is kind of a joke slide. I had no idea that this happened. I just tagged my tool on GitHub as using Capstone, and then I guess the guy who wrote the Capstone engine found it and tweeted about it, which is cool. All of a sudden I had like 10 followers on GitHub, which I was like surprised by. But yeah, so let's go at the end. Any questions? Yeah.
Sort of a clarification question about the operating tool. I was wondering if there's a, correlation between each, like dereference with the B table that was right next to it. I guess I'm wondering if there's a connection.
Oh yeah, no, yeah, definitely a good question. Let me go back. So make sure I understand. You're asking like, does let's say this value here contain, like, does this address here contain this V table pointer?
Right. I guess I'm just wondering how those two are connected, the V table to the value.
No, yeah, that's a good. So no, that's a good question. So here in the value column, this is the value that is currently in ESI, and then it does the V table identification starting with this value, the 1269, and it finds that the value that's at this address, if you interpret the value in ESI as an address, this is the value that's currently located at this memory address, which my tool thought, oh, okay, it's probably a V table. So yeah, no, there's a direct one-to-one correspondence where if there's a value in the V table column, it's because that is the value, like the value at the address in the value column appears to be a V table pointer. Does that answer your question?
I think so. I guess, and then for the values that don't have, I guess, a V table next to it, it's because you didn't find, I guess, the same permission relationship.
Exactly. Yeah. So it failed that check of does it look like, does it have the same memory protections that a V table kind of pointer chain would have? So that's a really good question. Yeah, you can see actually that most of the objects, most of the data structures traversed in this sequence were virtual objects, as best as our tool could determine. So occasionally you come across some that aren't virtual. Like, I don't know, whatever's here is not a virtual object, apparently. So Yeah, same with this. We would probably not expect our, coordinates in memory to be a virtual object. They might be, they are inside of a virtual object. But obviously, the float value -254 is not a pointer to a V table, so it left that blank there. That was a good question. Yeah.
So I got two. Have you ever read Game Hacking by Nick Cano?
Yeah, I picked that up a couple months ago, actually.
Yeah,
that's a great
all
book.
the same stuff. It was really cool.
Yeah, so I think his book talks a little bit about pointer scanner.
Yeah.
I think that might have been how I found out about pointer scanner, and I was like, oh no,
Oh yeah.
someone scooped me by now. Yeah.
That's awesome. The second one was, have you ever thought about contributing your code for this tool to Cheat Engine or to improve that? I don't know if it's open source now.
Yeah, Cheat Engine's open source as far as I know. I haven't thought about it, maybe. One of the things I actually already thought about was Nick Cano, the author of the game hacking book, is writing a memory scanner in C++. I thought this would be a good feature. I haven't reached out to him or anything like that, but yeah, I mean my code's on GitHub, so anybody's welcome to use it. And it might be a good thing to integrate into existing tools, existing more fully featured tools. So yeah. Yeah.
So as you were working on this tool and looking at other tools and stuff, did you happen to find any that are able to kind of infer what types of data structures are present in the relationships between them? Like you can start following pointers and you can say, okay, this looks like a linked list and these are typically this long versus a doubly linked list. Try to just kind of grok the structure stuff.
So are there tools out there that do that?
Yeah,
sort
have you
of thing?
seen stuff doing that already?
Actually, so the memory scanner that Nick Cano is writing on GitHub, the README says it will attempt to determine lists and map structures and stuff like that. Yeah, so I haven't used it, but yeah, that's the only one that I've seen that does that, which, I mean, yeah, that's awesome functionality, so
Okay.
if it does that, that'd be really cool. Yeah. Any other questions? Oh yeah, way back.
So, in order, practical use of your app there, your program, do you have to start the game first and then that, or do you have to start that first and then the game?
The order doesn't matter. You do need to have, you're going to have your game running before you, enter in the process ID of the game and the address from the game that you're interested in. It doesn't necessarily matter the order in which you start the tools. You just need to have the game running as soon as you enter in, the process ID and the address that you're interested in. At that point, the tool will attach itself as a debugger to your target process and start doing its work. So
some games they won't run properly, or they won't run at all if you're trying to use a debugger, run an debugger. Do you have the same issue with your program, or does that somehow get around that?
So Battlefield 2 doesn't do any sort of debugging detection or mitigation like that. So luckily I haven't had to do anything around that. I know, like you said, a lot of modern games do that. I guess that would be up to whoever wanted to use the tool to find a workaround for that. But I guess on the bright side, there's a lot of people who are going to try to figure that stuff out just so they can use a regular debugger. If you can figure out how to get a regular debugger working with a particular application, this tool should also work.
Just to expand upon the last question a little bit, especially online games, a lot of them nowadays incorporate anti-cheat.
Oh yeah.
Valve does this a lot, and one thing that you want to watch out for is if you try and do something like this with a game that has anti-cheat, like BAC specifically, if you even have Cheat Engine installed on your computer, regardless if it's running or not, you can receive a ban for that.
Oh wow, okay.
So that's definitely something to watch out for.
Yeah, so I've never worked with a Valve game, so I've never had to come across that, but yeah, that's good to know. Yeah, I guess it kind of depends. It's user beware, I guess, Try to do whatever you have to do to avoid detection.
Yeah, there's some pretty sophisticated cheat out there.
Definitely. Yeah. Yeah.
What would you do to kind of defeat tracing like this if you were writing?
That's a good question. I thought about it a little bit. I haven't come up with anything I don't
you
like
use some
that.
kind of control flow letting type thing where you have to hit these addresses before you do
Yeah, I don't really know. I don't really know. I know a lot of games come packed, the packed executable. I don't think that would stop this because it's just, if the instructions execute, it's gonna record them and be able to analyze them. So I don't know, maybe some sort of obfuscation at the instruction level would throw capstone for you, but actually probably wouldn't throw capstone for loop. It would probably throw my analysis logic built on top of capstone for loop. But I don't know. I haven't really tested it much outside of Battlefield too. So that's a good question. Yeah. Any other questions? We're out of time perfectly. So thanks everybody.